Okay, let's jump right in. We're talking about these tiny plastic particles today, nanoplastics and microplastics, or NMPs.
Right.
They're showing up in places you might not expect, like, well, our tap water.
It's quite pervasive. There was a study recently, wasn't there? It looked at tap water globally.
Yeah, exactly. 14 different countries. And get this, out of 159 samples, they found these plastic bits in 129 of them.
Wow, that really drives home how widespread this is becoming.
It does. And, there's growing concern because some research hints that ingesting these NMPs could potentially cause issues.
Yes, things like potentially disrupting our gut microbiota, maybe links to insulin resistance, even affecting liver function. It's still early days research-wise, but the concern is there.
Right. So, given these tiny plastics seem to be pretty common, we decided to explore a recent study looking at a really, maybe a surprisingly simple way to cut down our intake from tap water.
And that simple method is...
To boiling it, plain old boiling.
Ah, interesting. Yes, that study specifically looked at how well boiling works for the most common types of NMPs found in tap water, things like polystyrene, polyethylene, polypropylene.
So, for you listening, our mission today is to unpack this research. Can this everyday habit, boiling water, actually make a real difference to how many of these tiny plastic particles we're exposed to?
A very relevant question.
Okay, so let's get into it. Where are these NMPs even coming from? How are they getting into our drinking water in the first place?
Well, the study highlights that they're present in the actual sources, both groundwater and surface water, like rivers and lakes.
Before it even gets treated.
Exactly. And the problem is, while our traditional water treatment plants are good at removing lots of things, they have limitations, especially when it comes to the really, really small particles.
The nanoplastics.
Yes, those ones smaller than 1 micrometer. They're particularly tricky to filter out completely with current standard methods.
So the usual filtering isn't quite enough for these tiniest bits. Now, the idea of boiling water for safety, that's not exactly new, is it?
Not at all. It's a traditional health practice in many parts of Asia, for example. It's well known for killing off bacteria and viruses and removing some chemicals, too.
So the researchers thought, well, if it works for those things.
Could it work for NMPs? That was the central question they tackled.
And the answer seems to be yes, at least sometimes.
A qualified yes, based on their findings. The key discovery was that boiling hard water with calcium carbonate levels above 120 milligrams per liter, can remove a significant amount.
How significant?
At least 80% of the polystyrene, polyethylene, and polypropylene NMPs they tested, covering sizes from 0.1 up to 150 micrometers.
80%. Just from boiling. How does that even work? What's the mechanism?
It's actually quite fascinating. They pinpointed a process called coprecipitation, specifically with calcium carbonate.
Okay, calcium carbonate, that's the stuff that causes limescale, right?
Exactly, the scale you find in kettles. When you boil hard water, the higher temperature causes calcium carbonate to form, or nucleate, basically right onto the surface of the NMPs.
So the little plastic bits act like seeds for the scale to grow on.
Precisely. The NMPs get encapsulated, trapped inside these growing calcium carbonate crystals, or incrustants, as the study calls them.
Like tiny cages forming around the plastic.
That's a good way to picture it. And these NMP-filled scale particles then become heavy enough to settle out or get caught if you filter. The study actually shows images, fluorescence images, electron microscope pictures confirming this encapsulation.
Wow. So does that mean the harder the water, the better it works? More scale, more trapping?
That's the trend they observed, yes. They tested various hardness levels. Removal went from about 34% in moderately hard water, around 80 milligrams per liter,
Okay.
up to 84% at 180 milligrams per liter, and even hit 90% removal in very hard water at 300 milligrams per liter.
90%. That's impressive. But what about people with soft water? Less calcium carbonate, so does boiling do anything then?
Interestingly, yes, it still seems to help, though maybe not quite as dramatically. Even in soft water, which they classed as below 60 milligrams per liter, they observed over 25% removal.
Huh. So it's not just the scale formation then?
Apparently not entirely. The researchers suggest that even without much scale forming, the high temperature itself might cause the NMPs to sort of clump together aggregate and then simply settle out due to gravity.
Right. The heat itself encourages them to stick together.
Yeah.
Makes sense. Okay, what about the amount of plastic? Did the concentration of NMPs in the water matter?
They looked into that too, using polystyrene nanoplastics of different sizes. The good news is the removal efficiency stayed pretty high, mostly between 80 and 97% across a typical range of concentrations you might find in tap water.
So for most situations, boiling should still work well,
Generally, yes. They did note a potential issue if NMP concentrations were extremely high, like over 1 milligram per liter.
which is unusual.
Yes, the study suggests global tap water concentrations are typically well below that level. But if it were that high, the amount of calcium carbonate formed might not be enough to trap all the plastic. You'd still remove a lot, but maybe not 80–90%.
Okay, so for most people's tap water, boiling should be effective regardless of the exact concentration, within reason. Now, you mentioned the type of plastic, but the study also looked at their surface properties. That sounds quite technical. Why is that important?
It is a bit technical, but it affects how the plastic interacts with the minerals. They tested polystyrene NMPs with different chemical groups on their surface, some bare, some with carboxyl groups, some with amino groups.
And did that make a difference?
It did, especially at temperatures below boiling, between, say, 25 and 90 degrees Celsius. The bare and the carboxyl ones, which tend to have a negative surface charge,
Okay.
showed better removal during this heating phase than the amino ones, which have a positive charge.
So negative plastics attract the positive calcium ions more easily, helping the scale start forming sooner.
That seems to be the thinking, yes. The positive charge on the amino NMPs might initially repel the calcium ions a bit, but interestingly, once the water actually reached boiling point, 100 degrees Celsius,
Then what happened?
at boiling, all the types they tested showed good co-precipitation. The high energy of boiling seems to overcome those initial surface charge differences. They also mentioned changes in something called zeta potential.
Which is like static charge?
Sort of, yeah. It relates to the repulsion or attraction between particles. As temperature increases, this changes, generally making it easier for things to clump together.
Fascinating stuff. What about the size of the plastic particles? Did smaller ones get removed better or larger ones?
Size also played a role, particularly as the calcium carbonate started forming around 80–90 degrees. For the negatively charged types, the smaller 0.1 micrometer particles were removed a bit more efficiently than the larger 1 micrometer ones.
Why would that be?
The thinking is that smaller particles have a much larger surface area relative to their volume.
So more surface for the calcium carbonate to grab onto initially.
Exactly, more nucleation sites. But again, the key point is that once the water was properly boiling, the process worked pretty well across the different sizes they tested.
Okay, so let's try and summarize this mechanism. We boil hard water.
Right. Heating breaks down bicarbonates in the water, increasing carbonate ions.
Yeah.
These react with the calcium ions already present in hard water,
And they form calcium carbonate.
crystals, which preferentially start forming on the NMP surfaces. The NMPs act as nucleation sites.
Got it. Then the crystals grow.
Yes, they
Mhm.
grow, encapsulating the NMP inside. Plus, the heat makes everything move around more, bumping into each other, Brownian motion, and the reduced repulsion means the NMPs and the crystals stick together more easily.
Heteroaggregation, they called it.
That's the term, yes. These larger clumps then become heavy enough to settle out.
So heat makes minerals stick to plastic, trapping it and making it fall out of the water. Simple, yet effective.
That's the essence of it, and they confirm this worked similarly even for slightly larger microplastics too.
Okay, so stepping back, what are the implications of this globally? If boiling hard water can remove, say, 80% or more of these common NMPs, that sounds like it could make a big difference to our overall exposure. So,
It could potentially be quite significant. The study did some estimations based on global water hardness data and average water intake.
and what did they estimate?
Their calculations suggest that people drinking boiled water might ingest 2 to 5 times less NMPs compared to drinking unboiled tap water.
2 to 5 times less. That's substantial.
It is. They included a map showing estimated NMP intake based on regional water hardness, highlighting areas where boiling could have the biggest impact. It really suggests this simple, low-tech approach could be a viable strategy for reducing exposure long-term.
Especially since it uses existing habits in many places.
True, although the researchers do note that boiling isn't universal. In many developed countries, drinking tap water directly is common. People might not be aware of this potential benefit.
Right. It does almost sound a bit too easy. Were there any catches, besides needing hard water and avoiding super high concentrations?
Well, the effectiveness naturally depends on the specific water chemistry and the types and levels of NMPs present, which can vary quite a bit regionally. So it's not a magic bullet guaranteeing 100% removal everywhere.
Okay, that's fair. So thinking practically, What are the key takeaways for someone listening who might be wondering about their own tap water?
I think the main point is if you live somewhere with hard water, boiling your tap water appears to be a surprisingly effective method for reducing your intake of these common plastics.
And they had some advice on how to boil.
Yes, they suggested considering non-plastic electric kettles or using a gas stove, mainly from an energy efficiency and emissions perspective, based on their supplementary analysis.
Okay, good tip. Avoid boiling in plastic. Use an efficient method. Anything else?
They also recommended maybe using a simple filter, like a fine tea strainer or coffee filter, when pouring the boiled water.
Ah, to catch the scale itself.
Exactly. Since the NMPs are trapped in the scale, filtering out the visible scale particles would provide an extra step to remove them from the water you drink.
Makes sense. You get rid of the scale, you get rid of the plastic strapped inside it.
Precisely. But again, remember, the effectiveness will vary based on your local water.
Okay, so let's wrap this up. The headline seems to be, boiling tap water, especially if it's hard, could be a simple, cheap, and surprisingly effective way to cut down on tiny plastics in your drinking water.
It really underscores how a traditional practice might offer a partial solution to a modern environmental health concern. Its accessibility is a major plus.
Absolutely. So for you listening, maybe this changes how you think about your tap water. Does knowing this make you reconsider just drinking straight from the tap, especially if you know you have hard water?
And it definitely raises broader questions about microplastics elsewhere in our environment and diet.
Definitely food for thought. Maybe check your local water hardness, consider boiling, perhaps filtering afterwards.
And it highlights the need for ongoing research, doesn't it, to fully grasp the health implications of NMPs and refine these mitigation strategies.
Indeed. Well, thanks for exploring this with us. Until our next deep dive.
Keep asking questions.